Hello and welcome to the ninth lecture on earthquake resistant design of structures. In the last lecture, we were discussing about an example that was showing us how to design the beam for ductile detailing. In this lecture, we would be discussing about how to design a column for ductile detailing. Continuing with the same example, now we will be designing it for the columns. Now we know what was the question. The question was that we had been given from 3 bay, and this was a 6 bay 4-story building, and in the ground floor there is a column C2. Now let's go for design of this column C2. So the first thing that we do is we do the design checks, and in the design checks we check it for axial stresses. So the factored axial load that is acting on this column from the calculation that we have already done is the amount of axial load that was acting on this column C2 is 144.56 kilonewton, and the factored one would be multiplied by 1.5, so it would be 216.8 kilonewton. If now the column is treated as 400 mm by cross 500 mm, depending upon the size of the base, we have taken the ratio of the column width into depth. The factored axial stresses would be 216,800 in terms of Newton divided by 400 into 500, so it will be 1.084 Newton per mm square. Now this is greater than 0.1 FCK, which is 0.1 into 20. So hence the design, we can now design it as column as per clause 7.1.1 of IS 13920 or 1993 or 2016. Now checking for member sizes, the width of the column would be is 400 mm. Now that's greater than 300 mm, hence it's okay as per clause 7.1.2. Now this is also as of IS 13920. The depth of the column is also limited by IS 13920 7.1.3 clause. Now here the depth is 500 mm, so B by D ratio is limited. It is 400 by 500, here is 0.8, but it's limited, it should be greater than 0.4. Now this is greater, so hence it's okay. Next comes the question of the span. The span of this column is 3150 mm. The effective length of the column can be calculated using Annexure E of IS 456-2000, the Indian Standard Code. In this example, as per table 28 of IS 456-2000, the effective length should be taken as 0.85 times the unsupported length, which is in between that of fixed and hinged case. Now L by D ratio would be 3150 minus 500. This is the depth of the beam, so we are actually defining the clear span into 0.85, which is making it the effective one, divided by 400, which is D. Thereby it's equal to 5.63, so it's less than 12. That's, we are designing it as a short column, hence okay as per clause 25.1.2 of IS 456. If it was a slender column, we would have to add the secondary moments and the drifting moments in the column. Now the minimum dimension of the column is 400 mm, which is greater than 15 times the largest diameter of beam longitudinal reinforcement, that is 15 into 20 the beam longitudinal reinforcement. For example, that if that's given to be 20 mm, so it is 300 mm, hence it's okay as per clause 7.1.2 of IS 13920. Now the third check that we have to meet, now this check was related to the member sizes, and it's again defined by the ductility requirements and the strength requirements. Now the third check is for the limiting longitudinal reinforcement. Now the minimum reinforcement that has to be provided as per IS 456 clause 26.5.3.1 is 0.8%. So here it's 0.8 into 400, which is the width, into depth, that's 500 divided by 100 in the percentage, with 1600 mm square, and the maximum reinforcement is 4%. That's limited from practical considerations. So this is as per clause 26.5.3.1 of IS 456 2000. So that's 4 into 400 into 500, the width and the depth, divided by 100, that's 8000 mm square. Now let's go ahead with the design of this column C2. Now the design of the column. Now the first thing what we need to do is that we need to calculate the the forces for column reinforcement at A, which is the bottom end, which is fixed, and this is B, which has got a beam up there. First approximate design is done, and finally is checked for all force combinations. In this case, what we have, that the moment above one axis dominates, and hence the column is designed as a uniaxially loaded column. The column is oriented in such a way that the depth of the column is 400 mm for X direction earthquake and 500 mm for Y direction earthquake. Now design for earthquake in X direction, first we need to calculate the forces. Now PU is the load, the actual load, that's 217.14 kilonewton, and MU is 420.69 kilonewton meter in X direction, that we have already calculated from the analysis for this column. So PU by FCK into BD would be 0.054, and MU by FCK into BD square, and these all terms are at the bottom, and this FCK into BD. Similarly here, these all terms are at the bottom, FCK BD square, it's 0.26. Now we know already FCK is 20, PU and MU values are known, B and D values are known now for these columns. Now referring to chart 44 and 45 of SP16, for D dash by D equal to 40 plus 25 by 2 divided by 400, which D, now this is D dash, it's equal to 0.13. We get P by FCK values from chart 44 and 45, that's the value is 0.14. Now the design for earthquake in Y direction, PU is 217.14 and MU here is 440 kilonewton meter. So PU by FCK BD again would be 0.054 and MU by FCK BD would be 0.275. Now referring to charts 44 of SP16 for D dash by D, which is equal to 40 plus 25 by 2 divided by 500 is 0.105. What we get from this chart 44 is P by FCK is 0.11. Now the longitudinal steel that we have to next determine, the required steel will be governed by the higher of the above two values, and hence we take P by FCK either 0.11 or 0.14. The higher one is 0.14. The required steel is 0.14 into 20, and that's 2.8%. Now because 20 is FCK, so P is 0.14 into 20, that's FCK, that's 2.8%, which is 2.8 into 400 into 500 divided by 100, that's 5600 mm square. Now we provide 10 25 mm bars and 4 16 mm bars, with the total ASC provided then would be 5714. Now that would be 2.85%. Hence what we are providing PFCK is 2.85 divided by 20, it's 0.143, which is greater than what is required. So once we have done this, next what we are going to do, we are going to detail the column. Now the detailing of the column, first thing is the detailing of the longitudinal bars. Now we know what we are providing. We are providing 10 25 mm bars and 4 16 mm bars. 10 25 mm bars and 4 16 mm bars that we are providing here. These are 4 16 mm bars and the rest are 10 25 mm bars. Now they are provided with cross ties here. Now these will be provided, these longitudinal bars will be running through the beam, because this is a continuous column. Then there is a column even above it, and it's an interior column, but the ground story ones, this is the footing beneath it. Okay, now once we have done this, what we are going to do, we are going to design the column for shear, the shear capacity of the column. Now what is the shear capacity of the column? Now assuming 50% steel is provided as tensile steel to be on the conservative side, thereby AST would be 1.43, because we have provided the longitudinal steel as 2.86%. Now permissible shear stress then, as per IS 456, if you check for 1.43% steel, for FCK being 20, tau C would be 0.7 megapascal. Considering the lowest PU, the value of PU is 217.14 kilonewton, what we get is the multiplying factor, and this multiplying factor is delta as per IS 456 clause 40.2.2, and this would be a value equal to 1 plus 3 into PU divided by AG into FCK, and this value would be 1.16. Now that would be less than 1.5, thereby considering the formula given in IS 456, the value of tau C is 0.7 into 1.16, that's 0.812 megapascals. So the effective depth in X direction is 400 minus 40 minus 25 by 2, that's 347.5 mm. Now VC is the shear capacity in the X direction, what we are determining first, thereby it would be tau C, that's 0.812 into 500 into 347.5 divided by 1000. Now here 500 is the depth of the beam and 347.5 is the width of the beam. Now this value would be 141.085 kilonewton. Now in the when we are calculating the effective depth in Y direction, this value would be 500 minus 40 minus 25 divided by 2. Now this value is 447.5 millimeters. Thereby VC is 0.812 into 400 into 447.5 divided by 1000. Now this value is 145.345. Now once we have determined the value of VC, the shear capacity of the column in X and Y direction, what we are going to do is we are going to analyze the column for the amount of shear that is acting on it in both directions, X and Y. The maximum factored shear force in X and Y direction is 217.14 and 200 kilonewton respectively. Now this has already been determined from the analysis that we have performed. The shear force due to plastic hinge formation at ends of beam, now that's the second thing that we are going to determine, and for this first we have to determine if the earthquake is acting in X direction, then the longitudinal beam of size 300 mm into 500 mm is reinforced with, there may be a beam running at the top. Now this is reinforced with 420 mm bar plus 516 mm bars, so a maximum of 1.74% at the top, and for example say it's 1.34% at the bottom. The hogging and the sagging moment capacities that are evaluated for this beam are 288 kilonewton meter and 221 kilonewton meter respectively. Now this beam is acting with the column. Now this is the column and these are the beams that are running across, perpendicularly across the beam. Sorry, this is the beam and this is the column that's running across the beam. Now what we know is that once we have the moment capacities for the beam known to us, the shear force corresponding to plastic hinge formation in the longitudinal beam would be VU is 1.4 MUBR plus MUBL by HST. That this amount is 1.4 into, now we know that the shear hogging and the sagging capacities of the beam are 288 and 221. So once we know MUBL and MUBR, the sagging and the hogging moment capacities, So we can determine 1.5 into 288 plus 221 divided by 3.15, which is HST. Now HST is the height of the column. That is, so what we get is the value of VU, that's 226.22 kilonewtons. Now earthquake acting in Y direction, the transverse beams would be acting. Now for example, if the beams that are acting here are 300 mm into 600 mm and are reinforced with 3 mm 16 mm phi and 5 number 20 mm phi and 1 number 16 mm phi, the total reinforcement that's provided is 1.485% at the top of the beam and 0.978% at bottom. So thereby we obtained the hogging and the sagging moment capacities as we obtained in the last lecture, and they are evaluated as 377 kilonewton meter and 246 kilonewton meter respectively. Thereby the shear force corresponding to plastic hinge formation in the transverse beam would be VU is 1.4 MUBR plus MUBL by HST. Now here MUBR is 377 and MUBL is 246 divided by 3.15. So the value that we are getting is 276.89 kilonewton. Now this is the value of the shear forces due to plastic hinge formation due to the earthquake in the column. Now in the Y direction, earlier we obtained along the X direction, and along the X direction it was 226.22 and along the Y direction is 276.89. But we also have the maximum factored shear forces in X and Y direction, that's 217.14 and 200. This is not due to the plastic hinge formation but due to the shear resisting forces and present in the beam, beam and the column itself. Now once we have known, we have analyzed the column for its capacity and analyzed it for the forces due to the that are acting due to the shear, due to plastic hinge formation and due to the factored shear forces in the columns. What we are going to do is we are going to design the column for shear. Now the design shear force for the column shall be higher of the calculated factored shear force, that is due to the analysis that we have obtained, and the shear force due to plastic hinge formation, now in either of the transverse or longitudinal beam. Now this is as per clause 7.3.4 of IS 13920. The design shear in X direction is 226.22 kilonewton. Now this is higher of the value of 217 and 226.22. that is, along the X direction we had this 217 and 217, and due to the plastic hinge formation the value that came was 226.22. so the higher value is 226.22. Similarly in Y direction we have the higher value of 200 and 276.89. 276.89 was due to plastic formation, and due to analysis along the Y direction the factored shear force was 200. So the higher value is 276.89. Now once we know the design shear forces along X and Y direction for which we have to design the column, now what we are going to do is we are to detail the transverse reinforcement in the column. So the first thing we do is we detail the links in the X direction. Detailing the links in the X direction would mean that we need to calculate the value of Vs. Now Vs is the shear forces that are acting when we are that are acting more than what is the capacity of the section. Now that would be V U minus Vc. Now Vu is 226.22 in X direction, 226.22 minus 141.085 is the shear capacity. That's the shear capacity here. 141.085 kilonewton is the shear capacity in X direction. So the value comes to be 85.135, and the spacing of the four-legged, if we are providing four-legged 8 mm phi links in the column section, what we are getting is the spacing as per we know this formula 4 into, now this is the area of the section, 0.87 into Fy into 347.5 divided by the Vs. Now so the value that we are getting is 263.76. Now similarly in the Y direction The value of Vs is Vu is 276.89 now in Vu direction, minus 145 is the shear capacity in the y direction, 145.348. So the value is 131.54, and the spacing of 3-legged 8 mm phi links would be this much. Thereby the nominal link would be the spacing of the hoop shall not exceed half the least lateral dimension of the column. That is, if we, apart from providing the transverse reinforcement, wherein this is the spacing, we also have to fix the spacing nominally, that is 400 by 2, that's 200 mm as per clause 7.3.3 IS 13920. So we provide 8 mm phi links at the rate of 200 mm center to center in mid height portion of the column. This value 200 mm is lesser of these both two values, 263 and 211. Thereby the nominal has to be provided rather than providing from this design calculation. Third, we have to also provide the confining links at the ends, which is the special confinement in the columns. The area of the cross section ASH of the bar forming rectangular hoop to be used as special confining reinforcement shall not be less than what we have, and it should not be less than, as per clause 7.4.8 of IS 13920, is H is the longer direction of the rectangular bar measured to its outer face, and this value that is coming is 500 minus 440 minus it's the value of H, and this is the value of AG here in this calculation. So what we are getting from this formula from 7.4.8, this is the gross area, AK is the core area, so we have subtracted the area of the dia of the outer section, and then FCK is known to us. H is the longer dimension of the rectangular link measured to its outer face, and this is what we are getting. And third thing is S is the spacing of the stirrups. Now ASH is the area of the cross section of the bar forming rectangular hoop. Now having known, assuming 8 mm phi stirrups, ASH would be 50 mm square. Thereby ASH would be 50 equal to, we put in the values here, H is 188.5, FCK is 20, AG the value that has been calculated here, 400 into 500, AK after subtracting the area of the the dia of the bar and the cover area, this is the value of AK that we get, and thereby S value is 83.75 that we get from this clause for the rectangular hoops. Now the link spacing for the confining zone shall not exceed. This is again as per clause 7.4.6 of IS 13920. It shall not exceed 1/4 of minimum column dimension, that is 400 mm by 4, that's 100 mm, but need not be less than 75 mm, not more than 100 mm. That's another clause. So we provide 8 mm phi confining links at the rate of 80 mm center to center, because what we need is at least 83.75. It should not be less than 75. It should not be more than 100. So what we are providing is 8 mm phi confining links at 80 mm center to center for a distance L0. Now this L0 we have defined in the earlier lecture for the confining zone, special confining zone. It should not be less than, as per clause 7.4.1 of IS 13920, it shall not be less than larger lateral dimension, that is 500 mm, and 1/6 of the clear span. It's 3150 minus 500 divided by 6, it's 442 mm, or third one is 450 mm. Provide confining reinforcement for a distance of L0 equal to 500 mm on either side of the joint. So we would be providing the maximum of all these, 450, 442 and 500. We are providing on either side of the joint. So this is what we are providing actually. Now this is a beam at the top. The column is running throughout to it's a continuous column, and at the bottom it's fixed with the footing being provided. So the column longitudinal reinforcement is running right into the footing, and then we have a development length here. But what we also have is that in the middle portion, apart from L0 from the face of this, L0 is the distance, the face from here. Similarly, L0 is the face from here. We might have an additional bar here somewhere. Yeah. Now this would be L0 and this would be L0. And then in this zone, the links are provided as confining reinforcement. In the middle zone, the links are provided as nominal reinforcement. Now in the confining zone, what is our reinforcement, the transverse reinforcement that we are providing? It's in the middle portion, it's 8 mm cross ties at the rate of 200 mm center to center. But in the confining zone, which is the top and the bottom zone, what we are providing is the 8 mm 5 bars at the rate of at the rate of 80 mm center to center for a distance of L0, which is equal to 500. It will be 500 from here and 500 from here. And rest, we also know that the special confining reinforcement is taken into the footing as well. We have already discussed that. And then there would be the beam reinforcement running parallelly. Now if the beam reinforcement is being provided in this zone, and if this is continuous, then there may be no need of providing the bars within this zone, and in that case we would have something like this, and the reinforcement being provided in such a way that this is the beam reinforcement that's running throughout, and then another beam reinforcement at the bottom. Then we would have some reinforcing bars that are running perpendicular similarly they would be provided in the other half of the now again we have discussed that there is a confining zone in the beams as well. So what we have, this middle portion, there is no reinforcing link provided in the continuous beam, continuous column joint. Okay, thank you.